want to talk about depth and size perception. So we've talked about the wet pathway. The wet pathway tells us about what we're looking at, objects, scenes, faces. And now we're going to look at the where pathway, the one that goes dorsal in the brain towards the top. And where we'll deal with depth and size and motion. All right, and so let's start with depth and size. So learning objectives. Now, so we need to be informed about the spatial arrangement of objects and surfaces in the environment. The challenge of this is that our world is 3D, but our retina is only 2D, right? And so how do we overcome that? That's the question here. Now take a moment and close one eye. Line up your left index finger with your right index finger, about 6 inches behind it. And then quickly switch which eye is open. Then switch back. Just go back and forth. And you should see your eyes moving, or see the fingers moving in terms of their relative position. Right? And the reason for this is because your eyeballs are in slightly different places in your head. Right? And so each eye has a slightly different view of the world. And the advantage of this is if we lose one eye, we got another one. And it just allows us to see more of the world. Okay? Because our eyes are in the front of our face, we get a certain amount of overlap in our visual field, and that enhances depth perception. Okay? In fact, that's the norm for predators. Right? For prey, like rabbits, birds, eyes tend to be on the side of the head. For predator birds, like hawks and eagles and owls, the eyes are more towards the front of their face. Okay? Now, for predators, the advantage is that the overlapping visual fields give a better chance at spotting prey and better chance and better accuracy in terms of swooping down and getting that prey if you're a bird, if you're a hawk coming down on top of a snake, say, or a rabbit. Okay? Whereas eyes on the side of the head give you a bigger world, right? You can see further around you, and since predators are usually sneaking up from your side, it gives you a better chance of seeing them. But it cuts back on depth perception. Okay, so let's talk about how we see depth. Okay, this is just a 2D picture, and yet we can see depth in it. There's cues that are available in here that help us see, how far away the mountains are from where we're standing, and how the trees get further and further in the distance. So one possible cue just comes from movement of our eyes. All right, when you can just take your finger, hold it out, and as you bring it in, you should feel your eyes kind of come together if you're staying focused on the eye, and if you stay focused on the finger, and if you move your finger out, you should feel your eyes come apart. All right? And there are tiny little muscles that are responsible for flexing your lens. Okay, and so it's possible that those muscle movements add to our sense of depth perception, but it's probably not. Probably don't rely on them. They probably don't have that much impact, but they might. For the most part, though, depth perception is a mix of one-eyed and two-eyed cues, monocular and binocular. So let's focus on the monocular cues first. All right? And here's a list of them. I'm about to go through them. Okay, here's a pirate, got a patch, only one eye, and you can close one eye and you still see depth. Okay, so monocular cues are actually probably the predominant way that we see depth. Okay, even though two eyes gives us an advantage to it, we still can rely on just one eye. So interposition or occlusion is simply the idea that we see whatever's in front as being closer than whatever is in back. Clearness atmospheric perspective is the more foggy or hazy things are, the further they look behind. This is actually from the same spot, and you can see how much closer those look than what's there, because of the clear sky. Shading and lighting, we expect light to come down from the top, and you can see that Microsoft takes advantage of that to create depth in its images by darkening the sides and lightening the top. This is what allows us to see kind of the craters on the moon. Another cue is familiarity. We know the size of things. We know what things look like. Right? And so seeing these horses, it might look like they're further away than they are. They're actually ponies. Wild ponies, and they got very short legs, so they're actually very close to me. And same with this, we know how size of hands versus the rest of the body. But this is from the Rodin Museum in Paris, and Rodin made on his figures they had huge hands and huge feet, which kind of throws off that perspective. Relative size, right? If these were the same size, they're not, but if they were the same size, we would expect the smaller one to be further away than the taller one. Another cue is what's called texture gradient. The further back, the denser the texture gets. This is in Tunisia. This is a graveyard for French soldiers in World War II. Okay? But you can see as the crosses go back, they get denser and denser. So we know that that's further back than up here. Elevation, things that are higher, okay, or we see as further away than things that are lower. Perspective convergence, just as things get further away, they converge, get closer. Yeah, this is in Paris. All right. So here's some ruins in Tunisia. These are some Roman ruins, and a number of different cues, and I'll give you a second to kind of figure out what some of those are. Yeah. So we'll have familiarity and relative size. This woman, the mother of our host in Tunisia, and texture convergence, height, atmosphere. You have a number of different things in here. And the same here. This is a very wet street in Paris. Think about what cues you see here. And this one, you should see the square in front of the triangle, in front of the circle. It's occlusion and height. All right, so now line up your index finger in front of your nose and move, just one index, and then move both index fingers, excuse me, one behind the other, and then move your head back and forth, okay? And you should see both move, right? But one is probably moving faster than the other. Okay? The one in front should be moving faster and bigger range than the other one. Okay? This is called motion parallax. Okay? When things are in our environment are moving, the things closer to us appear to move faster than the things farther away. Okay? Okay, so those are all monocular cues. Let's look at our two-eyed cues. Okay? And for the most part, this has to do with what's called binocular disparity. Right? So unless something is right in front of our nose, okay, it's going to come to each eye at different angles. Okay? Right. And because of that, the view in one eye will be slightly different in the other eye. Okay? You can see how these are posted are positioned in the environment. As they come into the left eye, they're going to look further apart than when they come into the right eye. Okay? And somehow, through a process called stereopsis, our brain is able to integrate that disparity into giving us depth. This is really one of the great mysteries of how that happens. Okay? We know it does, but we don't know exactly how. So, stereopsis is the perception of depth that results from binocular disparity. Okay? It's if you had a 3D ViewMaster, okay, that's how it worked. Right? It had two images, one coming to each eye, and they were pictures that were taken at a slightly different angle. This is also what happens in 3D movies. There will be two cameras at slightly different angles, and one will film through one type of filter, and the other will film through another type of filter. Okay, and so that's why when you get 3D glasses, one will be red and one will be green or blue. I forget the two colors. Or if you have the 3D glasses that look like sunglasses, they're polarized, and one is polarizing light at a horizontal angle, and the other is polarizing it at a vertical angle. Okay, so we have two slightly different angles and two slightly different filters, and that gives us the perception of 3D, even though we're watching a 2D movie. In the same way that our eyes are creating a 3D image from a 3D image from a 2D retina. Okay? We won't worry about the correspondence problem, but when people start having when they, due to different disease processes, brain damage, other sorts of things, people can have problems with stereoscopic acuity. Okay, this is where two eyes can get in the way. That our brains aren't able to actually integrate that disparity, and that leads to greater car accidents, slower hand-reaching movements, and slower walking. Okay, this is one of the things researchers were interested in. Is depth innate, or does that develop? And it's apparent at very early ages, and this is called the visual cliff. There's glass right here, but the texture is the same all the way across. So if there's depth perception, then they should see that what's on the bottom is further away than here. If there's not, then it will look like it's all one thing, and they'll just keep going. Depth perception, there should be some hesitation. And all animals, they've done this with all kinds of animals, even elephants are able to see depth, which shouldn't be too big of a surprise. And they do it from a very young age. Okay? But in testing this, it's been pretty clear that all you need is one eye. All right? That it's mostly monocular cues that people are using for depth perception, and from a young age. That doesn't mean that you're not scared walking along a glass bottom when the world is way, way, way below you. All right, size perception is basically dealt with the same way as depth perception. Okay? They're very, very much linked together. Okay? Now, one important idea is the idea of size constancy. Even though, if we're looking at, say, a family member walking away, going off to their car and, waving goodbye and all that, even though they're getting smaller, all right, in our visual field as they go across, we recognize that they haven't changed size, that they're still the same size. Okay? And that's called size constancy. And that's important, all right, because otherwise the whole world looks like it's shrinking as it moves away. Right? So we're keeping that constant. One theory behind the Muller-Lyer illusion is that it's size constancy gone wrong, that It's these arrows going out rather than in that gives that illusion. All good illusions are difficult to explain, so that doesn't fully account. People have kind of found alternative ways to explain that. But that's one way to look at the illusion, one possible reason for it. Okay, there we go. Waiting for my GIF to get active. These lines are actually the same size. Okay. But this one looks a whole lot bigger because, you know, our cues for depth perception say that things should get closer and closer together as they go back. But because that line is not doing that, it's not obeying the rules, then we swear they're different. And even though now you've seen that because those red lines come up, this still looks smaller than that. Okay? In fact, there's quite a bit of discrepancy there. Okay? But this shows the relationship between depth and size, how we're using similar cues for both. All right, the moon gives us a real life illusion of size. Okay, when it's low in the horizon, the moon looks huge. When it's high in the sky, it looks small. The moon is actually the same size, same distance from the Earth, whether it's low in the horizon or high up in the sky, and so it should look the same, but it doesn't. Okay, and again, like all good illusions, it's a very difficult thing to explain. One explanation is that because when it's low in the sky, we have these things to compare it to, whereas when it's up high, we don't. But again, that doesn't fully explain the illusion. All right. This is another real-life illusion, and that things can look at different sizes depending on where we're standing. This is a mountain in Washington State, yeah, and it's Mount Hood, and it's over 14,000 feet. And this is my friend's backyard, and you can see it looks really close. It is. They're not that far from it. If you go into town, which is about a mile up the road, this will look even bigger, okay, which makes sense. But actually, according to my friend, I didn't actually see this. If you go a couple miles away from the mountain, there's this one spot you can stand on, and it looks even bigger than it is. Okay? All right. So, kind of depending where you are and the surroundings and other things, it can fool our sense of size and our sense of closeness as well. All right, so your homework here is to take a picture and identify cues for depth in that picture. Okay.